Okay. So next part of my talk will be this Ionospheric response to space weather event, and I go again to this gas space process cartoon for space weather. We have drivers different from not only solar ultraviolet radiation, and during this event, in the Earth's atmosphere, generated structures different from nominal condition, different from normal atmospheric climatology. And it's again a reason for radio wave propagation disruption. And main phenomena, specific phenomena, it's geomagnetic storm. And this event occurred when geomagnetic Earth's geomagnetic field affected by solar wind plasma, solar wind magnetic field, and occurred event like reconnection when magnetic tube become open, and it's initiate massive precipitation of aurora particles, produce aurora which extended from normal aurora pole to toward equator, can cover mid latitudes. It's of course it depends of magnitude of geomagnetic storm, and for some cases it's aurora can be seen on latitude 50 degrees and moreover. And typical geomagnetic storms have several phases, like initial phase, sudden storm commencement, main phase, recovery phase. It's formulated by Iurii Cherniak, and one of characteristics it's disturbances of Earth's magnetic field, and this field disturbed due to increasing of ring current, which have opposite sign than geomagnetic field. It's compensate Earth's magnetic field, and following it's also produce more particle precipitation because particle reflection altitude depend of Earth's magnetic magnitude. And storm can be characterized by different indices, and main set of indices most commonly used. It's sorry. It's KP index. It's equatorial based magnetic index, and it's varied from its logarithmic and varied from a range from 0 to 9. Use it for characterization. 9, it's big magnetic storms. And another index, it's disturbance storm index, DST or SIMH. It's different scientific groups call this index, but different way. And it's measure intensity of ring current, which depresses geomagnetic field. And another index, it's auroral electric jet, and which characterize auroral zone magnetic activity, current which flow around auroral oval, and but of course also available important characteristic of space weather, like geomagnetic field Z component, velocity of solar wind and solar wind pressure, like combination between density of solar wind and speed of solar wind. And what we have during geomagnetic storm, we have modification of density, electron density, composition, circulation in near Earth's atmosphere can persist several days. And two kinds of ionospheric response for the geomagnetic storm can be formatted. It's positive ionospheric storm. Then we have positive deviation from normal, quite non-disturbed day, and respectively, it's negative day when we have depression in ionospheric plasma globally or on some altitudes. So, mechanism which explain positive geomagnetic storm is increase density of oxygen and also important properties that if we have meridional winds and we have magnetized plasma, plasma pushed up to high altitude when we have low recombination rate, and at the same time, eastward electric field can push up ionospheric again up to area with low recombination rate, and for geomagnetic storms, also important. It's downward atmospheric plasma transport from upper altitude reservoir, the traveling atmospheric disturbance, and plasma distribution due to distributed electric field, because we have penetration of electric field from magnetosphere that disturb global circulation. And for negative storms, it's mainly caused by decrease in ratio molecular oxygen, atomic oxygen, nitrogen, like similar to cases of winter anomaly. And I will focus on one representative storm which occurred in 2015 on maximum solar activity cycle, and it's was very large. Stronger storm was only in 2004-2003, and during the storm was really intensive particle precipitation, and as I said before, aurora during this event was appeared in mid latitudes. And here a ratio from GOVI instrument for several days of before the storm, main phase, and recovery phase. For 5 days, we have as normal distribution, some decreasing in high altitudes, but for main phase and for recovery phase, we have decreasing of O and 2 ratio during today, with some recovery on next day. It's rather long processes. And for ionospheric condition, we can see snapshots of electoral content derived from IGS global ionospheric maps, which represent general overview of plasma redistribution. And here it's white condition. Here storm was developed, and we have two effects. Some effects in equatorial anomaly, redistribution of equatorial anomaly peaks to high latitudes, and after that we have negative phase of geomagnetic storms when plasma density, overall plasma density in ionosphere go down. We have disappearance of equatorial anomaly crest and general decreasing of density during this particular day. And this snapshot of total electron content observation in different sectors, and storm started when in American sector was local day and local time, local night in Asian, and you can see sequence of positive effect on American sector when plasma density increased on up to 20% in the daytime, some effect in time in African sector, but it's from mid to subequatorial latitudes, and strong depletion in up to several times in Asian sector. We have practically no electron content for 1 day and more. So it's two-phase, positive and negative wave for one geomagnetic storm, and it's big storm, but we still should take into account even minor disturbances. This case for rather minor geomagnetic storm, this magnitude 16 Tesla, which produce very strong positive ionospheric response. For mid-latitude station, we have increasing of total electron content more than up to 100%. It's important because, for example, for navigation purposes, ionospheric delay, which produced by this total electron content, mitigated by some models, and if models embedded in some GPS receiver not reproduce this event. It's obviously not reproduced because it's based on climatology. We can get error in positioning due to this additional ionospheric delay. And this redistribution of plasma density for this event derived from IGS Inox maps. You can see enhancement anomaly and positive effect on longitudes, wide range of longitudes, and this effect concentrated mainly on high altitudes, more than 200 kilometers. So it's topside effect, which confirm explanations that plasma pushed up to altitudes with lower recombination rates. And also important features of geomagnetic storms, it's new energy which pushed over the ionospheric system, and this energy from paper ground glue consists from particle precipitation and electromagnetic energy. And from electromagnetic energy, most important energy comes from Joule heating. What is physics of this events? It's global electrical circuit when we have like source of electric like electric source in magnetosphere, and this closed on ionosphere because it have some conductivity. It consists of like whole, Peterson, and parallel. It's, this circuit closed in altitude on altitude around 100-150 kilometers, and within our oval. And this formulation of conductivity for different direction, because it's tensor conductivity, and I should note that Peterson whole conductivity peak, it's around 120 kilometers. And if we looking on ionization rate, ionization production by particle precipitation, we can also see that exist some peaks on particle precipitation. If we have particles with different energy, peaks occur from 90 kilometers to 130 kilometers. And for typical aurora, we have energy range within 3 to 8 electron volt, and it's again altitude around 120 kilometers. And here, one of sample of such effects. Here we have European sector with electron density profiles derived from cosmic observation, from radio occultation, and in blue color you can see sequence sets of profile for this region during quiet time, and red its profile during geomagnetic storm, during strong particle precipitation. So in this area, on altitude around 100 kilometers and a little bit higher, density increased up to several order, and source of this ionization is particle precipitation, and in this area we have increased ionospheric conductivity, and sequence its intensification of current and energy releasing. And one effect of this heating, it's the excitation of traveling atmospheric disturbances, because we have additional source of heating which push plasma both sides, and mainly toward equator. And this samples for explanation of traveling atmospheric disturbances, how it can be detected by ground-based ionospheres. We have variation in altitude and density, and these structures have horizontal scale more than 1,000 kilometers and propagate with speed up to 1,000 meters per second during these disturbances. And here, visualization of traveling ionospheric disturbances derived from global network of GPS receiver. We have total electron content, observations, and remove background TC in order to derive disturbance component. So we can see excitation of travel cancer disturbances on our border and propagation toward equator, and it's can propagate even through the equator to opposite hemisphere. Some waves can emerge around the equator. So it's a global scale phenomenon which can exist several hours, and how it's looks with overall electric jet index, which some proxy of Joule heating. You can see variations of our electric jet this time, and it's diagrams like slices of maps that I presented previous slide. You can see how it's propagate from longitude about 70 degrees toward mid latitude, and how it's merged over equator here. So it's evidence of propagation this structure to opposite hemisphere. And here results of simulation from TGCM model, here also delta TC, disturbed component of total electron content, and energy formulated like our energy flag. It's assimilated from IME procedures. It's developed by Arthur Richmond Anchor, and you can see that all these waves propagated from high latitude toward equator appeared when we have increasing our energy flux. So it's clear dependence of the excitation of this wave through the our heating due to field currents and Joule heating. And here, focusing on European latitude, it's another event. It's December 2015. So we have distinguished propagation of terminator and propagation of traveling cancer disturbances. For this case, we combine two approaches. First, it's detection of ionospheric traveling cancer disturbances from DC disturbed component, and second, it's analysis of large scale, not large, but medium scale irregularities appearance in our area of high latitude. It's also based on GPS, but another processing was done, and field line currents magnitudes delivered from ampere magnetometer observation. It's magnetometers on board satellite flight on altitude 800 kilometers. And one of products, it's field line currents estimated from magnetic field disturbing component. And the same how it's look in ground, this signature of that component of magnetic field on several high to mid latitude station. And for this case, we found that excitation of this wave occurs exactly on border the area when equatorial border of our oval can be detected from irregularities observations, and also from all models. So we can estimate when and where these waves appeared and how it propagates with time and space. And another interesting large-scale structure which developed during geomagnetic storms, it's multitude storm enhancement density. First, it was reported by John Foster on base ground-based GPS and incoherent scatter radar observation, and it looked like strong TC enhancement, like continuous size enhancement in TC, the same in plasma density on F-layer peak, and it's driven by neutral wind pushing plasma up, and driven by convection, which enhances during magnetic storm, which takes this plasma and transported it around a circulation cell. It's like sketch how this plasma can be uplifted by wind, particular, and electric field. So plasma uplifted on area when we have low recombination rate, and this dense plasma transported by magnetic circulation projection, like here from noon to dusk, and opposite direction. And this sample, one case, early study, when we have its polar view, we have enhancement plasma, circulation cells, it's so-called Tonke ionization, very narrow area with very dense plasma, which can be different from ambient plasma on one order, for example, and it's transported through the polar cap, and next it's separated to polar patches, which transported to dusk sector. It's the same convection, but derived from super dark observations. And for case of storm in December 2015, we observed such effects both in GPS genesis observations, like the total electron content maps, and also from satellite orbit, when we have superimposition of circulation cells, total contact measurements, and exact, like in the previous case, we have propagation of set structures through the polar cap and separation of polar patches. And on higher altitudes, it's enhancement in tech units, because on high altitudes, it operated on altitude about 700 kilometers. Normally, we have no plasma above satellite, but when satellite flies through the structure, we have very dense plasma this like area, just exactly this Tonke of ionization. And here simulation of TGSM model, when model simulate storm time enhancement density, one point the TGSM and its first principle model, which include both neutral and ionospheric parts, and this output of model in TC, and you can see that pattern of storm time and instrument density and tone of ionization looks practically the same in simulations. So when we can put to the model input pre-storm condition and take total content in mid-latitude and overall altitude, we can successfully simulate effect of propagation of these disturbances through the globe. Because only in observations we cannot trace all the structure due to lack of data, but for asymmetric model simulation, we can reproduce this ionospheric features. And other important topic, other important problem of ionospheric response during geomagnetic storm, it's occurrence of ionospheric plasma irregularities. Nominally, irregularities exists in two regions: equatorial ionosphere and highly ionosphere. Equatorial ionosphere, it's mainly quiet time phenomena, which have climatology that I talked before. For high latitude, we have background irregularities, which not related with disturbances, but during disturbances, these irregularities can significantly intensified and appeared on mid-latitudes in sub-equatorial latitudes. And equatorial plasma bubbles also can be impacted on geomagnetic disturbances and atmospheric disturbances. And for case of plasma bubbles and related irregularities, we can see disappearance, suppression of bubbles, and excitation of bubbles in different time, different region than in normal climatological distribution. So for irregularities detection, exist several techniques. I focusing on trans-ionospheric GPS links and one parameters that can be derived from the signal. It's rate of TC and rate of TC index. It's variation of ionospheric delay in time and space. And this technique allows to use normal geodetic receiver and numbers of such receiver distributed globally, and data from these instruments available for public. And how looks irregularities detected by this approach? This rate of TC for station Kiruna. Here we can see quiet condition, here disturbed, and practically all links, because every line, it's one links between ground-based station and particular GPS transmitter. And when we have disturbances, practically all links affected by irregularities and phase scintillations. So for this particular time, we can expect disruption of navigation solution or degradation of position. And here it's IGS rate of TC maps, which represents variation of scintillation of irregularities activity over northern hemisphere. We developed for Ionospheric working group, and you can see evolution of irregularity over in time and space. It's every maps correspond to one particular day when we integrate all station over northern hemisphere, and due to particle precipitation, we have plasma structures, plasma gradients, which can be detected by a rate of TC index. Similar way, like we have phase simulation here, and for this map, clear scene evolution of border, equatorial border of irregularity all from day to day. And if we look on dynamics of equatorial plasma irregularities driven by geomagnetic storm, we can, of course, we can't cover all areas global, but here evolution of irregularities all for northern southern hemisphere, for storm on March 2015, you can see how from beginning storm it's start move toward the equator, extend, and intensity of irregularities essentially increased. So this GPS GNSS approach, how to trace these structures, and it's one of source of information about irregularities and dynamics. And it's important that irregularities overall sometimes enhancement density and tone of ionization. It's a related phenomenon because it's plasma gradients and turbulence inside, and on diurnal maps you can see clear overall, but in main phase of geomagnetic storm we can like structure from which oriented from noon to dusk, and it's corresponded to our overall. This structure corresponded to sometime enhancement density and tone of ionization and polar patches. And next day, you can see absence of this structure inside polar cap. So if we superimpose maps which give us information about irregularity occurrence and total electron content, we can see that this area is enhancement, plasma enhancement, due to particle precipitation, and it's the same. We have plasma structures within oval. Here, we have storm enhancement density and starting of tonic ionization motion. We can see full irregularities of overall field, and in this plot we can see transporting of tonic ionization material through the polar cap, and irregularity signature. Here it's like some kind of visualization of circulation cells when plasma transported along here. And irregularities for high latitude and irregularities during magnetic storm, it's a little bit different, because for nominally for high latitude it's particle precipitation on lower ionosphere, but for case of enhancement density and signatures, we have enhancement in topside.
ionosphere. This redundancy profile from cosmic observation, we have peak not like normally on F2 layer, but altitude like 300, but practically into time higher, it's 600 kilometers. And for observation, for in-situ observation from satellites, this plasma probe, it's two swarm satellites, we can see the density enhanced in up to 10 times or more against surrounding ionosphere. It's clearly seen in this observation when this peak exactly between lobes of this circulation cells, and density of plasma which propagated from one side to another side on high altitudes can become persistent several hours when it's transported from one side, from north side to dark side. And another problem, another feature of geomagnetic storm, its impact on low latitudes irregularity occurrence. So this global map, of course, you can see features of our overall, but in the same time, here you can see appearance of irregularities over equator with different phase of storms. Here, our electric jet and IMFDZ index, and for this particular case, we have practically suppression of ionospheric irregularities. This first several hours, we have normal plasma bubble, post-census plasma bubbles development, and when storm progress, we can see plasma bubbles appearance on Asian sector when there was no in quiet days. The same here. And this bubbles persisting up to local midnight. And here we expect some bubbles in American sector, but practically nothing for this particular day. And this recovery phase of geomagnetic storms appeared bubbles which persist a long time and also persist morning time bubbles when we see sunlighted ionosphere, which obviously should feel this depletion by plasma ionized. But here we have negative phase of geomagnetic storms. We have electric fields penetrated from magnetosphere, and we have vertical winds, vertical plasma motion, which drive this bubbles resistance during practically all night up to morning hours. And another interesting feature of plasma bubbles development during magnetic storm, it's appearance plasma bubbles, which very high apex altitudes, which can reach European latitudes. Here, South Europe and North Africa, and you can see signatures of several plasma bubbles which affected this area. Of course, next hours it's become significant on American continent, it's first time when this equatorial type structures and corresponding irregular scintillation appeared over Europe. It's a more detailed view of this phenomena. It's sequences of rate of TC maps for European sector and the same for American sector. And it was penetration of electric field, which caused uplift of equatorial ionosphere, and on equator was huge bite out, practically no plasma over equator, and for sub-equatorial and mid-latitude, plasma bubble formed and identical magnetic field. And for American sector, these structures reach up to sub-auroral latitudes and persist several hours. And if we looking in observations, in situ observations on altitude 500 kilometers, we can see huge bite out, huge depression of plasma within around geomagnetic equator. It's rather wide. It's about more than 10 degree in latitudinal range, and appearance plasma bubbles which developed on mid-latitude about 40 degrees exactly on over Europe, and persist several hours. For American sector, we can also detect similar structure, but even bigger depression and more structuring in plasma density over American sector. And what we can see in this observation, we have two big depletion, very big depletion here, and following structuring in few hours, and extension of this plasma bubbles both sides of equator to the mid-latitudes. And this plots show appearance of very strong amplitude scintillation. It's detected by deoccultation from cosmic one. Normally, it's S4 index within 0.2, but for cases of strong plasma bubble development, we have very huge numbers of links affected by scintillation with S4 more than 0.5. It's a really big number, and it's again covered to zone in America sector and European sector. And for this particular event, it was reported degradation of positioning from EGNOS system. It's really evidence that this anomaly structure in Europe, which difficult to predict appearance irregularities from south. Normally, it's some degradation of positioning within high latitudes, comes from particle precipitation, but for this case, we have a lot of scintillation, a lot of amplitude scintillation, which disturb navigation links. And, another phenomena that can be occur during geomagnetic disturbances. And it's not very big disturbances. In May 2017, September 2017, its magnitude was about minus 159 Tesla. And both events, we have development of auroral, development of storm time bubbles, and next, these plasma bubbles involved in transport, similar to storm time enhancement density, like it's embedded in dense plasma over equatorial subequatorial latitudes, like here, formed depletion and formed channel of plasma stream with embedded irregularities, which pushed up to high latitudes and measured with irregularities produced by our particle precipitation. So it's one of first images when depletion irregularities are reached from equator merged with high latitude irregularities. And again, in this area, practically all this area, all American continent was affected by irregularities, scintillations, and for the 7th we can report again degradation positioning on ground and even on satellites with GPS receiver operated here. It's just not movie, just snapshot to explain this depletion, this stream depletion, surrounding irregularities, and trace of the structures from lower latitudes to practically to the our latitudes. So I would summarize it. This structure that I told, it's complex phenomenon driven by space versa. During storms, we have big amount of electromagnetic energy and particle precipitation, which lead to increasing Joule heating, disturb neutral dynamo, and during this all this event, important large-scale phenomena. It's storm enhancement density, topicalization, and traveling ionospheric disturbances. First set, it's like enhancement plasma on subequatorial latitude and motion toward polar cap and high latitude. LST, it's phenomenon which generated on border of oral and can propagate toward the equator and opposite hemisphere. Auroral irregularities which produced by particle precipitation during geomagnetic storm can reach mid-latitudes. Normally it's within 70 degree in magnetic latitudes, but can reach up to 40 degrees and seen on continental Europe and mid-latitude on US continent. And for equatorial region, storm time effect can suppress plasma bubbles, plasma irregularities formation like regular post sunset, but induce plasma bubbles in different sector, not typical for this season, and in different local time, like post midnight and morning and even daytime plasma bubbles. And it's evident that this irregularities in structures can affect performance of GPS positioning and also on some channels of trans-ionospheric communication. I remember one paper when was links between U.S. military was disrupted by plasma bubble during operation in Afghanistan. So it's important to know and try to predict these effects. Thank you.
Are there questions? Many questions before, no questions now. Okay. You are around. We can also keep chatting with you during the...
Oh, yeah.
Well, Ivan, you have...
Okay,
Yeah, of course.
Iurii, another great talk, of course. So you mentioned that during the storm time, the plasma is pushed, maybe pushed right upward, where the recombination rate, of course, is. So that's looks like positive effect over there.
yes.
Up. Wouldn't be negative effect on the bottom side of the ionosphere where the plasma was evaporated into the...
It's depend of local time. If we have some solar ionization, this plasma can be still produced, and it's like if we move some plasma, but we have neutral.
You still have neutral.
Yeah.
Other questions? Okay, Sean.
So you're speaking about affecting performance on GNSS positioning during the bubbles. Has there been any study recently that has demonstrated the impact of having more than one constellation now? Because most of the studies are based on GPS only. What happens if you have at the same location GPS and Galileo and Beidou? What does that? How does that improve your situation?
I consider that if we have more links, these links with different geometry, and receiver can give solution from different constellation separately, it can improve because probability to.
But that's what intuitively I would say so. But has it been published? Is there a study?
I don't know such publication. I worked with this topic, and yes, mainly we work with GPS, but it's the same band.
Sure.
Only different for this particular time. What geometry we have, and for example, for satellites with low inclination, satellites constellation like GPS have more probability to be affected than, for example, GLONASS, which have more like polar war constellation. So, but it's interesting topic and should be studied. At least I think it can be important for future Galileo satellites. Maybe make sense to place it on different inclinations.
Any other question?
Maybe I have a small comment with respect to the question by Sean. There are actually cases, for instance, in the Brazil, South American sector, in which the plasma bubbles are so spread, so large, so diffuse that almost all satellites in view are affected by scintillation. That's an issue from practical application for sure. So I don't know either. There are publications about those kind of events, how rare they are, but they are not so rare.
Yeah, and now when we come to the high solar activity, numbers of bubbles that we detect from cosmic observations rise in several times. So probability in this particular region to be all system be affected, it's rather high.